Um, yeah, hello everyone, and thank you for the introduction, and thank you for inviting me to this technical session. My name is Evgeny Rezunov. I'm a PG student from the Institute for Communication Technologies and Embedded Systems at RWTH Aachen University in Germany. And today I'm going to give you a presentation on our work titled Automatic Microarchitecture-Aware Custom Instruction Design for RISC-V Processors. This is the work that we published in a paper that just got accepted for the upcoming ICCAT conference. I think in the event description on the website you can find a link to a preprint in case you want to also read it. Let me start with some motivation for our work. Why are we talking about processor customization in 2025? The problem is obviously not new. There has been ongoing effort in the last 30 years of finding the balance between the flexibility of general purpose processors and the efficiency and performance of dedicated hardware. You've all probably heard of the term ASIP, or application-specific instruction set processor. So these are processors that take such a general purpose processor as a baseline and extend it with some custom instructions that are tailored to provide efficiency for certain applications. But today, with the success of RISC-V, this topic seems to gain relevance again, because RISC-V is an open instruction set architecture. It is also inherently modular and extendable. There are lots of standard extensions, for example, for vector operations or some bitwise computations, but also there's a lot of research and work in the industry towards custom RISC-V instruction set extensions. Although RISC-V offers this great platform for custom processors, the customization itself is still a very complicated process that is typically done manually. Even if we define these custom instructions in the instruction set architecture, such as RISC-V, another challenge is to integrate those into a real processor, into real hardware. So the question that we are addressing in this work is if RISC-V processor customization can be automated. And to answer to this question, I'm going to start with some high-level background information on processor customization and on automating this process. Then I will present our tool called CIDRE, or Custom Instruction Designer for RISC-V Extensions. We wanted to have a catchy name for the paper. Then move on to some results and finally provide a short summary and some future research directions. So let's look at a small motivating example that you're all probably familiar with. This is a multiply accumulate instruction, and essentially it consists of a multiplication followed by an addition. You can find such operations in a variety of workloads, from digital signal processing to machine learning. So basically everywhere where we have matrix vector multiplications or matrix-matrix multiplications. And if we assume that we have a baseline processor that supports both of these primitive operations, multiplication and addition, we can fuse them together to get a custom multiply accumulate instruction. And the idea here is, instead of executing two separate instructions, we can execute it in one, so we get performance gains from that, provided that the operation is seen frequently in the target workload. So how do we find such custom instructions? The first thing that I want to introduce here is some theory and on data flow graphs, because this is usually the level at which custom instructions are defined. So data flow graphs are directed acyclic graphs for each basic block of a software application. Basic blocks are just sequences of instructions that have one entry and one exit point in our application. So this is a nice way to separate the application into blocks. And each basic block or each DFG consists of vertices, which are our instructions, so in this case, RISC-V instructions, as you can see, and edges that represent the data dependencies between those. So as you can see here, for example, the result of this multiplication here is used as a source operand in the subtraction there. That's why we have an edge between those two operations. In our representation, we extend this by also giving a notation of the operand order here. For example, for subtraction, it is important if one of the operands is source operand 1 or 2, as subtraction is not commutative in general, but for operations such as multiplication, at least functionality-wise, nothing changes if we swap these two. That's why we have an asterisk there. There are also some additional vertices and edges for inputs and outputs, which can be either registers, as you can see here, or immediate values. And a custom instruction in this context is just a subgraph of this data flow graph. So if you want to automatically find such subgraphs that we can use to define custom instructions, in the literature there are usually 3 steps to do that. The first step is called instruction enumeration. In this step we find valid candidates for custom instructions. So here I'd like to show you a small example. Of course, we cannot just take any vertices, combine them. Yeah, this is our custom instruction. There are some constraints that guide this process. For example, some instructions can be, some operations can be forbidden. Let's take this load word instruction, for example. So in many works, memory operations such as load and store are forbidden because the custom instruction unit, custom functional unit does not support memory interfacing. Another constraint is, if we look at this example here, we have 3 inputs. So inputs are just vertices that have incoming edges into our custom instruction subgraph, and 1 output. Outputs are vertices in the custom instruction subgraph that have outgoing edges. And this number can be also limited by, for example, the number of register read and write ports and by the instruction encoding. So with these constraints in mind, the result of the instruction enumeration can look like this for this basic block or for this DFG. So we will have another custom instruction candidate here. Again, 1, 2, 3 inputs, 1 output. And another one here, again with 3 inputs and 1 output. After we've enumerated these custom instruction subgraphs or like candidates, the next step is isomorphism detection. The name itself might sound a little cryptic, so I'll just show an example to explain it. Let's look at 2 subgraphs here. If we look closely at these ones, then we can see that both perform the same functionality. So we have an OR operation, an AND operation followed by an addition, and the same you can see here. And if we define custom instructions, then it would be correct to define just 1 custom instruction for both of these equivalent subgraphs. And the way to identify such equivalent subgraphs is isomorphism detection in graph theoretical terms. So after we've enumerated all subgraphs and classified them into equivalence classes, which represent our custom instruction candidates, the final step is instruction selection. So here you can see the result of our enumeration. As you can probably guess, our job is not done here, right? So the first thing is that we cannot define an arbitrary number of custom instructions. This number is usually limited. The second issue here is that the subgraphs that we identified have conflicts between them. So here we have an overlap, and we cannot just have all three at the same time. And so this is the goal that we have in instruction selection. We want to select a certain number of instructions or equivalence classes, and then cover the corresponding subgraphs so that we can maximize the performance gain in our target application. So for this example, optimal instruction selection would look like this. So we select subgraph 1 and subgraph 2, and this is basically the result. So now that I've shown you some background information, I would like to introduce our tool and also delve a little deeper into each aspect that I just presented in the background slides. So our tool looks like this. We take a RISC-V binary compiled from our baseline processor as an input. We pass it to generate data flow graphs that I mentioned on the previous slides. Another input that we take for our tool is some profiling information containing information about how often each of the basic blocks is executed. This information can be gained from an instruction-accurate simulator. Then we take these DFGs and feed them to the instruction enumeration step that gives us all the valid subgraphs with some user-defined constraints that we take as an input. Then from the valid subgraphs, we need to identify the equivalent ones that would correspond to the same custom instruction. This is done by the isomorphism detection step. So then we have these equivalence classes, and from these we need to perform instruction selection. However, in our tool, we don't just work on this abstract data flow graph representation. We also try to integrate the custom instructions into a real processor to get this microarchitecture-aware approach. And to do so, we create a processor model with a language called NML. Then we feed it into Synopsys ASIP designer that can then generate an RTL for our processor automatically, which we then can synthesize to get some area and latency values and use them for the instruction selection. On the next slides, I will explain why we do it and also explain each of these steps in some more details. So let's begin with the inputs and the parser. So as I already mentioned, the first input is our RISC-V binary for the baseline processor. Our tool supports 32 and 64-bit RISC-V with some general purpose extensions. And the second input, as I already mentioned, is the profiling information with the basic block execution counts from our target software application. And as I already said, we can get this information from instruction-accurate simulators such as Spike, for example. And from this information, we generate data flow graphs that are annotated with the corresponding execution count. Then as for the instruction enumeration step, I would like to give you some more details on the constraints that we use. So the first very important constraint is convexity. Again, this is a term from graph theory, but it is easy to explain on an example. So convexity means that there can be no path between two vertices of a subgraph that include vertices from outside. And here's an example. So if you look at this subgraph here, at first glance, it looks like a perfect custom instruction candidate. However, if you look at this vertex here, you can notice that there is such a path, as mentioned here. So from this add-I operation to an add here, we have a path that contains an operation from outside. And what it basically means is that if we defined this subgraph as a custom instruction, then its inputs would depend on its outputs. So it means that you cannot physically use such an instruction. So this subgraph is invalid because it's not convex. The next constraint is forbidden instructions, as I already mentioned. And as for our tool, we ignore load and store operations because of the more complex memory interfacing, and also control from instructions such as jumps and branches. Next, we have our input-output constraints. These are limited by the register file ports in our target hardware, and also by the instruction encoding. I will go into detail here a little bit later in our talk. But here I can show you some examples. So if we take this subgraph here, it has 3 inputs and 1 output. One of the inputs is an immediate, as you can see, so just a constant value. And one small detail that we noticed while implementing instruction enumeration is that we can treat such immediates both as inputs that need to be basically put into the instruction encoding, and also as hard-coded values. And why do we want to do that? So the reason is, if our input-output constraints limit the number of inputs by not 3, as in this example, but 2, then the subgraph here would be invalid, right? However, we can solve this problem by including the number 2 here into the instruction. Then we only have 1 output and 2 inputs. So we lose some flexibility because now this custom instruction will only match the subgraphs that also contain a 2 in them. But we can still define this subgraph, and it's better than nothing at this point if the constraints are stricter. Then, speaking of the algorithm that we use, we decided to use exhaustive search, which means that we enumerate all possible subgraphs complying to the constraints. Some other methods in the literature do it in a different way. They, for example, only take maximal subgraphs or already try to perform some kind of selection at this step. But we decided to take this one to have more flexibility in the subsequent automatic custom instruction generation steps. So we took an algorithm from the paper that I referenced here. You can also find the reference in our paper. And the problem with such an exhaustive search is, of course, the high number of subgraphs. So pure in theory, since we can include or exclude each of the vertices that we have in our data flow graph, the number is exponential. However, due to the constraints, this number can be significantly limited, and we can also use the constraints to efficiently prune the search space. So let's see how the algorithm works. I won't go too much into detail here because you can read it in the paper if you want, but here's just a very simple example to give you an understanding of how we can enumerate such instructions. So what this algorithm does, it reverses the data in reverse topological manner. It means that for any edge that we have in a subgraph, the target to this edge has to be visited before the sources. So yeah, simply said, we just go from the bottom of the DFG to its top. And we start by single nodes and then extend them by neighboring nodes that are filtered using some filtering function that takes convexity constraints into account. To this node, we can, for example, this one here, and this would be a valid custom instruction candidate. So we have 1, 2, 3 inputs, 1 output. Then we can extend this subgraph by the third node here again, 1, 2, 3 inputs, 1 output, and so on and so forth. So here you can see another example where you start from here. Then we can add this vertex here, which would be a valid subgraph. And then we can add this one here. And as you can see, the output constraint is violated here. So we have 2 outputs and only 1 is allowed. And the good news here is that we can also stop the search from this subgraph here, because due to the fact that we are going from the bottom of this of the DFG to the top, there won't be, the number of outputs wouldn't decrease if we go further to these nodes here. So this is the basic idea of the algorithm, and in the end we get all subgraphs complying to the constraints, from which we can then choose the best ones in the subsequent steps. So the next step, after we have all the valid subgraphs, is to define equivalence classes, so find all subgraphs that have equivalent functionality that would correspond to the same custom instruction. And the main challenge here is that isomorphism checks are exponential, so they're exponential in the number of nodes. The larger the subgraph, the more complex the check is. However, what we decided to use in our work is a different approach from just standard isomorphism checkers that already exist. So the approach is called graph canonization. Here is a reference to the paper where we got this idea from. And the main idea here is that for each subgraph, we create a unique representation. Unique means that for any subgraph implementing the same functionality, this representation here will be the same. So this is a graphical representation, right? We have a AND operation, then an OR operation, followed by an ADD, 3 inputs, 1 output. And it turns out our second isomorphic subgraph corresponds to the same canonical form. Of course, in the algorithm itself, it isn't a graph, it is rather a ordered list of vertices and edges of the subgraph, and these are ordered in a way that this representation is unique for all isomorphic subgraphs. So there are 2 main advantages to this approach. The first one is that if we have n subgraphs, we only need to construct this canonical representation n times, and then the comparison of these lists is trivial. Instead of doing a quadratic number of comparisons between all the enumerated subgraphs. Another advantage is that we can use this canonical form as a hash in a sort of a hash map where we can store the subgraphs and their unique representation. Another small detail here. So as we were implementing this approach for our tool, we noticed that there can be functionally equivalent instructions that have different input-output configurations. So here's a small example. As you can see, we have the same functionality here, so 2 AND instructions followed by a subtraction, but the inputs and outputs to these instructions are different. So in the first example, we have 4 dedicated inputs and 2 outputs. In the second example, one of the inputs is shared between the 2 nodes here. And in the third example, we only have 1 output instead of 2. However, if we assume that, or if the input-output constraints are 4 inputs and 2 outputs, we can use the same instruction to cover all these cases. So if we use the original algorithm, this would all result in 3 different canonical forms. However, what we can do is also just define this one corresponding to the first graph here. And as you probably know, in RISC-V, in some instructions, the output can be discarded by just passing the hardwired 0 register to it. So this would cover this case here. And if we want to use the same input, this is also trivial. We just need to pass it twice. Yeah, so moving on, we have identified the subgraph candidates and classified them into equivalence classes. Now comes the instruction selection. And as I already mentioned, the goal here is to select a user-defined number of most profitable instructions, or equivalence classes, as we learned from the isomorphism detection step. And there are multiple challenges in this step as well. So the first one is that the subgraphs conflict with each other. So here you can see 3 subgraphs overlapping with each other. Another case that we can have is cycles. So this is relevant if we allow disconnected subgraphs. Here's an example. So we have 2 subgraphs. They both consist of 2 instructions. And since they provide inputs for each other, it leads to a kind of a deadlock situation. So if we would, if we define them, or if we try to schedule them in the real application, this wouldn't work. So this is another kind of conflicts that we can see. Another challenge is that code selection on directed acyclic graphs is NP complete. It's very complex, so exact solutions are computationally expensive, and we need to resort to heuristics mostly. Finally, I mentioned that we want to select most profitable instructions, but how do we define the merit of such a custom instruction? So how good is a candidate that we are looking at? And this is the question that I want to address on the next slide. So mostly in literature, I mean, we talk about performance gain as our instruction merit, and mostly in literature it's defined as the difference between the so-called software latency and hardware latency. I will show you this on the example. So in our example, let's assume that every instruction takes exactly 1 cycle to execute. Then before the customization, the whole basic block would take 1, 2, 3, 4, 5 cycles to execute. Then let's assume we have 2 custom instructions here, subgraph 1 and 2. And for the first one, if we executed both of these operations in software, each of them will take 1 cycle. So the software latency is 2 cycles. And for the second custom instruction, again, we execute each operation in 1 cycle. So the software latency for this whole subgraph is also 2 cycles. Now, if we define these as custom instructions, then we will only have 2 vertices here. And again, assuming that both of these vertices execute in 1 cycle, the hardware latency, or the latency of executing the same operations as 1 custom instruction implemented in hardware, is 1 cycle here and 1 cycle here. So after customization, the whole basic block would take 3 cycles to execute, which yields us the speedup of roughly 1.7. Of course, basic blocks have different execution counts, so this merit value has to be scaled correspondingly, and this is the reason why we need profiling information as an input to our tool. And using this profiling information, we can prioritize the hotspots. So if there is a basic block that is only executed once, it doesn't matter how good our custom instructions are that we implement there if there's another basic block that is executed a million times. It turns out there are some problems with this simple view on custom instructions performance gain. So first, what is the impact on the critical path of the processor? Can we assume that any custom instruction takes one cycle to execute on our target hardware without making the processor slower? So for example, can we put 5 multiplications after each other and then expect them to be able to execute in one cycle? Probably not. Another question is the impact of the custom instructions on the microarchitecture of our processor, and we have multiple aspects here, but some examples are if we add some complex instructions, does it change the decoder logic of our processor? Does it make it more complex? Another aspect is pipelining. So if the processor is pipelined and we have a custom instruction that takes, I don't know, 2 or 3 cycles to execute, do we also need some synchronization logic there? So due to these aspects, we decided not to focus on this purely abstract software representation of basic blocks and data flow graphs, but also try to integrate the custom instructions into a real processor and see what the impact on the microarchitecture and critical path is. So here's the algorithm that we used for that. In our work, we do assume that each custom instruction takes one cycle to execute. However, we use synthesis to measure the impact on the microarchitecture and confirm that this is actually feasible. So we take our custom instruction candidates, integrate them into a processor model defined in the language called NML. I will go into that into details here a bit later. Then we use Synopsys ASIP Designer to generate RTL, synthesize it, and then look at the exact values and see if there's some negative impact on the critical path that would negate the whole performance gains that we estimated. So here's the selection algorithm. I won't go too much into detail here. You can also find it in our paper, or if you have questions, we can discuss it after the presentation. But yeah, essentially, the process is described here. And the next question is, how exactly do we integrate our custom instructions into the processor? So here's a short scheme showing that. So let's say we have this enumerated subgraph in a basic block of our application here. Then for the subgraph, we have a canonical form. Here's a graphical representation of it. From the canonical form, we know how many inputs we have and how many outputs. With this information, we can integrate this custom instruction into RISC-V instruction set architecture by selecting a suitable instruction template. I will explain this a little on the next slide. So let's say we call our custom instruction custom.isn, and after we integrated the instruction into the ISA, we also need to modify the microarchitecture, so add some kind of a custom functional unit that performs the functionality described here. And to do that, we use an architecture description language called NML. This is not the only option that you can use. There's also Codal. The idea here is that these architecture description languages operate on a higher abstraction level than, for example, Verilog, and they also facilitate the automatic generation of hardware that we can use for our estimates. So let's look at the custom instructions that we define. As I mentioned, we have several templates. 5 exactly, that we define in this architecture description language called NML. The templates have different numbers and types of inputs and outputs. For example, the first one has 2 source registers and 1 destination register, which resembles RISC-V R-type instructions. We also use a custom opcode here as proposed by RISC-V standard. Another option is, again, 2 inputs, 1 output, but one of the inputs is not a register, but a 12-bit immediate, as you can see here, which resembles the I-type instructions in RISC-V. Another option is 3 register inputs and 1 output, which looks like the R4 type instruction used in some in floating point extensions in RISC-V. The fourth option is we replace the third source register by a 6-bit immediate, which you can use for shifts, for example. And finally, the last instruction is a little different from other ones. It does not comply to RISC-V standard, as you can see here. So we don't use a dedicated custom opcode here. But since the baseline processor model that we use does not implement all standard extensions from RISC-V, we could use this encoding space to allow us to have 3 source registers and 2 destination registers. As you can see here, we also have a 3-bit field in every instruction that allows us to define up to 8 custom instructions per template. And as I already mentioned, the template is selected for each custom instruction candidate based on its input-output configuration, and then we can generate the functionality description from the canonical form that I showed on one of the previous slides. So now I would like to present the results and begin with the evaluation setup. So for our tool, we used 8 embedded benchmarks, 8 embedded applications from MiBench and Embench. Here is some statistics on the basic blocks in these applications. So on the x-axis, you can see the size of the basic blocks, so how many instructions are in each of them. And on the y-axis, you can see how much execution time was spent in each of these basic blocks as the percentage of the total execution time of the application. And from here, we can gain some interesting insights. So as you can see, most basic blocks are fairly small and do not consume a lot of execution time of the application, but there are certain outliers. So for example, for one of the applications, we have an extreme case, a basic block where more than 90% of the application execution time is spent. For some other applications, there are also basic blocks where 40 to 60% of the execution time is spent. So these are exactly our hotspots that we want to customize. Speaking of the basic block size, there is also some outliers. So most basic blocks are fairly small. However, we have some that are larger than 100 instructions. And for one of the benchmarks, we even had one basic block with more than 1,000 instructions in it, which offers some more potential for finding custom instructions. As for the baseline processor, we used one offered by Synopsys ASIP designer. So this is a 64-bit RISC-V processor with a 3-stage pipeline. It's an in-order processor. For the profiling data, we used an in-house instruction accuracy simulator. However, you can also use Spike with some minor adjustments to the way that the data is consumed by the tool. And as for the compiler, we used the GCC from the RISC-V GNU toolchain with the O2 optimization. So on the next slide, I will show you an example of a basic block from one of the applications that we used. As you can see, it was executed quite a few times. So it turned out it was one of the hotspots in the application, and our tool was able to find 2 custom instructions here. The first one is the red one here. You can see it here in this figure. It has 3 inputs, so 2 registers and 1 6-bit immediate, and 1 output. It consists of a shift operation followed by an XOR operation. And our tool suggests that the estimated cycle savings from implementing this custom instruction are 4.3%. And if we implement it as a custom instruction, then there won't be any negative impact on the critical path of the processor. Next instruction is a bit bigger. It consists of 4 primitive operations. This is also an example of why we sometimes want to use immediates as hard-coded values. So since we only have 3 inputs and 1 output here, we can still define this larger subgraph by using the immediates here as hard-coded values. And since the subgraph is larger, it also offers more cycle savings, about 13%, but it also has a larger negative impact on the critical path of the processor. So here are some more examples. Another subgraph or another custom instruction having 2 inputs and 1 output with 6 subgraphs corresponding to this instruction found totally in the application. This one would save 35% of the execution cycles and also have a minor impact on the critical path. Here's a larger example from one of the cryptographic benchmarks. It has a lot of shift operations followed by some logical ones. So this is how rotations are implemented. And this custom instruction would save 15% of clock cycles, and there were 24 such subgraphs found in the application. Here is this smaller example, so just 2 XOR operations merged together, but found really frequently in the application. And again, a larger subgraph with 3 inputs and 2 outputs, so the least restrictive case, and offering quite a big, quite a high performance gain. So here you can see the Speedup comparison for the 8 applications that we used, and we let our tool generate 8 custom instructions for 3 different input-output constraints. The Speedup is estimated as the ratio of application's execution time before and after customization. So we refer to the execution time as the number of clock cycles times the clock period. And as you can see, the highest speedup that we achieved was more than 2.4, so it was 2.47x for one of the cryptographic applications. And what is also interesting is that we had one case with negative impact from custom instructions on the performance. So we have a speedup of less than 1 in this case here, which means that our tool was able to find some custom instruction candidates that would offer cycle savings of, I don't know, a couple of cycles. However, the negative impact of implementing these instructions in hardware would completely negate the possible performance gain from these. So this highlights the importance of our microarchitecture-aware approach. Another advantage of our tool is that we can also use the generated RTL from the processor model to assess the area overhead from implementing the custom instructions. I didn't mention it on the previous slides, but area is typically used as the cost metric to show the trade-off between the performance gain that we have from customizing the processor and having a chip with a larger area. So here's a figure that compares both of these, so execution time reduction versus the area overhead for 8 custom instructions generated for different benchmarks. Of course, you cannot compare these values directly, because in the end, the priorities depend on the requirements to the design. However, we use this figure to show the different trade-offs for different benchmarks that you can have from implementing the custom instructions. So as you can see, some cases are very good. We have high speed up, for example, here and there, and very low area overhead. And for some other cases, the area overhead is much higher, and the speed up is not necessarily as large. So for these cases, it might not be as beneficial to implement the custom instructions at all. So in conclusion, we were able to see that RISC-V enables new opportunities in processor customization. And since the customization itself is a labor-intensive process done manually, this highlights the need for automation. And another important insight was that the microarchitectural details play an important role when designing custom instructions, and especially doing it in an automated fashion. As for the future work, one possible idea would be to have a broader customization landscape, so enable more complex instructions, including SIMD or instructions involving memory accesses. Another important aspect is compiler. So how do we customize our software for the customized hardware? And finally, simulation, which would give us some more accurate performance estimation, and also enable quick design space exploration with and without the custom instructions generated by the tool. Thank you for your attention, and I'm happy to answer your questions.
Yeah, thank you very much for the presentation. So we have a couple of questions in the chat, so I think you can go through them. We go. Starting with Ali. So first question is, how can the tool make sure there is no conflict in the encoding space of RISC-V? Yeah, that's a good question, by the way.
How the tool, sorry.
How can you ensure there's no conflict on the encoding space?
Let me go to the slide. So this is basically ensured by design. As I mentioned, at least for these 4 instructions, we use custom opcodes, so they aren't used by any other instruction, or they're not supposed to be used by any other instruction in the processor. As for the different custom instructions that are mapped onto the same template, we have this 3-bit field here that allows us to define up to 8 instructions that do not conflict with each other. So this case here is a little more complicated. As I said, it was only possible because our baseline processor model that we used to integrate these instructions does not use these encoding bits here. So this case wouldn't be, in general, possible for any RISC-V processor complying to the RISC-V standard. I hope this answers the question.
So moving on here, we do not have a lot of time, so I'm about to have a couple of good questions. Let me go to the second one from Ali. If there are somewhat similar subgraphs extracted, how intelligent is the tool to merge them and create a handful of custom instructions that will not add a lot of area? And then he provides an example there. I'm not sure if you want to go to the example in the chat.
Yeah, I can see the question. This is a very good question. I think there's some work in the literature of how parts of the custom instruction subgraphs can be shared between different instructions so that we do not have a high area overhead. As for our tool, we do not take this into account, so it is not intelligent enough to do this. I think the only benefit that we might get here is what the synthesis tool offers. I think it can still synthesize the hardware in a way that the area is utilized more efficiently. But as from our tool side, there isn't any feature enabling that. But this is actually an interesting question that, some works answer in the state of the art.
Great. So we have now a question from Saad. If CIDRE could be adapted for security applications.
Currently, we haven't thought about this. Maybe that could be an interesting direction for related work. I'm not so familiar with security applications, so that's why I cannot really answer this question directly. So here we're talking more about the functionality and how we can merge different primitive operations together to get some custom instructions. I think in the end, how the instruction is implemented in hardware is a different question. And again, some aspects of memory are also not yet covered in our tool. But I think that could be one possible direction for future work.
We have another question from Saad here about how modular is CIDRE and if that can be somehow reused, or the isomorphisms, the technique can be reused in other hardware design.
So this is actually one of the big advantages of our tool. So as you've seen, the algorithms that we used for instruction enumeration and isomorphism detection are not, so we adapted them from the literature. However, the design itself is modular. So in theory, we could exchange the components and take other algorithms. As for other hardware design workflows, I mean, this could also be possible, I guess, because for some some works approach this in a different fashion. They kind of do the whole enumeration and selection in one step, and as for our tool, the steps are completely separated from each other. So I mean, not without any adjustments, but I guess we could reuse them for other flows as well.
I believe one more question from Domingo. If you have analyzed the critical path of processors and how does the critical path affect the clock speed?
So this is the reason why we use this workflow here. So we try to synthesize the whole processor model to see if the processor with the custom instruction integrated into it can be still run at the same clock speed, or can be still synthesized for the same clock speed than the baseline model. And if it's not the case, then this negative impact can completely negate what we gain from decreasing the number of clock cycles through the custom instructions. So we don't do it, we do it in an automatic fashion from the synthesis tool. So we don't look at the instructions themselves and say what the impact would probably be. But since we synthesize the processor with the instructions, we get this information about the impact.
I'm not sure if I have any other. So, folks, any more questions? So we have 2 minutes. Yeah, I'm not seeing more questions showing up. So I think that's it for today. So I'd like to thank you a lot for presenting. So it really kind of a technical work, and I'm not sure if you are aware, but we have within RISC-V International SIG that works on custom instruction. Maybe you should consider joining that SIG to discuss some of the work, or see what they are planning on custom instructions for RISC-V. That would be a good place to connect with them. I can share with you later via email the details about that SIG and what they are doing. But again, thank you very much for joining. Thank you for presenting the work. I really appreciate that, and yeah, it was really good presentation. So, Finn, if you will, so feel free to show up in another RISC-V technical session.
Yeah, thank you very much for inviting me.